A 10 model A, let's see, sofas, right? And then 12 model B sofas and 5 model B sofas, right? This is in blue. Now the chairs are going to be 15 model A, 12 model B, and 8 model C. So this is how it can be organized, right? On data, the data organized. Also, we can also use tabulate the data, which will be like this in this form here, like an invoice. This is a furniture, and across is a model. Okay, this can also be organized in a matrix. Okay, this is a matrix. Rows. These are the rows. They refer to the sofas and chairs. And the vertical, the columns, refers to the models, which is A, B, and C. Okay, so this is how data can be organized. Okay, now what a matrix is. For example, matrix A, right? This is the capital letter represents the matrix. Example, matrix A, matrix B, and the smaller case letters, they're called the elements. For example, this means element A, right, which is our first column. First row, first column. Element A, first row, second column, and so forth. And then going down is also same thing, right? It's going to be 21 means the second row and first column, and so forth. Okay, again, this is like like another picture of the matrix, right? These are the rows across, and these are the columns. And like I said earlier, this is the element. A11 means this means matrix A, right? That's why it's capital. This lowercase letter, which is A. The first number means the row. The second number means the column. So this is element A, first row, first column. Element A, first row, second column, and so forth. So this is called the position of an element. 11 means first row, first column, like I just mentioned earlier. A14 means first row, fourth column. A23 means position is row 2, column 3. Okay, now let's do like a little exercise here. So what is the position of the following elements? A13, right? So A13 means first row, third column. This will be my first row, and my third column will be the position of a 3. A24 means second row, fourth column. So this is my second row, and this is my fourth column, which will be the element 8. Okay, now this is called the dimension of a matrix. It's called rows by columns. The number of rows times the number of columns. So for example, this matrix here, right? These are 2 rows, right? The ones that are across, and there's 4 columns. So the dimensions of this matrix is a 2 by 4. Example 2, determine the dimensions of the matrices below. Okay, the one to the left, right? There's 3 rows and 3 columns. This is called a 3 by 3 matrix. The matrix in the middle, there's 3 rows, 1, 2, 3 across, right? And 1 column, so it's going to be a 3 by 1. The last one on the right, there's only 1 row, right? 1 row and 3 columns, so it's a 1 by 3. Okay, now determine the order of the matrix. Can somebody they're in the audience, can they tell me the order of the matrix? If you want, you can put it in the chat, or you can just get on the mic and just say it. What's the order? How many rows? 1, 2, 3, 4. Right, it's going to be a 4. How many columns? 1, 2. So it's a 4 by 2. Okay, now this is called matrix operations. In order for you to add or subtract matrices, they have to be the same size. Okay, if they're not the same size, it cannot be done. Example, A plus B means, right? It means that we're going to add matrix A and matrix B, right? So we have to add, for example, the matrix A, right? The location, which is our first row, first column, we have to add it to the 1 on B, also first row, first column. That's why it's called A11 plus B11. And then we continue on the same format. Right now, we're going to add the first row, second column on A matrix plus the first row, second column on the B matrix, and so forth. You keep going until the matrix ends. Right? You just keep going. Now this is a second row, first column on A matrix plus second row, first column on the B matrix. Okay. And you keep going all the way till you finish all the rows and the columns. Okay. Now this is a definition here. Matrix addition. The sum of two M by N matrices, which is matrix X and Y, is a M by N matrix on the X plus Y, in which each element is the sum of the corresponding elements of X and Y. This is the example that the definition means, what I just showed you, where it says A plus B. And also for subtractions, it's going to be the same thing. Okay. Now let's do some actual examples here. Example 3 is matrix A, matrix B, matrix C, and matrix D. So first, we have to get the size of each matrix. Matrix A is a 2 by 3, right? Because we have 2 rows and 3 columns. Matrix B is the same thing, right? 2 by 3. Why? Because we have 2 rows and 3 columns. Matrix C is a 2 by 3, right? I mean a 2 by 2 because we have 2 rows and 2 columns. And same thing with matrix D. Okay, now, can we add A plus B? Right, so A plus B, right? We can do it because they both are the same size matrix. So to follow the definition, I'm going to add the first row, first column on matrix A plus first row, first column on matrix B. So it's going to be, the value is going to be 1 plus 8. And then negative 3 plus 0. And 2 plus 1. And then we go down to the second row, 2 plus negative 1. And then 2 plus 3. And then negative 1 plus 4. So here's my result, right? So 1 plus 8 will give us 9. If you want, guys, you can go straight from A plus B, right, from these two matrices on top to the answer. I just showed the work here just so you know exactly what's taking place. So negative 3 plus 0 will give us negative 3. 2 plus 1 is 3. 2 plus negative 1 is 1. And 2 plus 3 is 5. And negative 1 plus 4 is 3. So that's my result. Now let's add C plus D. First of all, can it be done? C plus D. Let's check the size, right? The matrix C is 2 by 2. And the matrix D is also a 2 by 2. So the operation can be done. And again, we follow the same format. So it's going to be 5 plus 2 and 1 plus negative 1. Now we go to the second row, negative 4 plus 9 and 3 plus negative 7. And here's my result. It'll be 7, 0, 5, and negative 4. That's my result of adding the matrix C plus D. Now let's do another one. How about A plus C? Matrix A is a 2 by 3, right? And matrix C is a 2 by 2. If you notice, matrix A and matrix C, they're not the same size. So in other words, this cannot be done, not possible. Okay? And I repeat, in order to add or subtract matrices, the size of the matrix must be the same. Now let's try subtraction. Again, matrix A is a 2 by 3. We're doing the same matrices as the previous slide. This is a 2 by 2 and a 2 by 2. So A minus B will be, we're doing the same thing, right? But instead of addition, it's going to be subtraction. So it's going to be 1 minus 8, negative 3 minus 0, 2 minus 1, and 2 minus negative 1, 2 minus 3, and negative 1 minus 4. So there's my result. It's going to be negative 7, negative 3, 1, 3, because 2 minus negative 1, right? The two negatives, or the minus negative, turns to addition, so it'll be 3. 2 minus 3 is negative 1. And negative 1 minus 4, right, is going to be negative 5. So that's my result. Now let's try C minus D. So it's going to be 5 minus 2, 1 minus negative 1, negative 4 minus 9, and 3 minus negative 7. So 5 minus 2 is 3. 1 minus negative 1 is 2. Negative 4 minus 9 is negative 13. And 3 minus negative 7 is 10. So this is the answer for the operation on matrix C minus matrix D. Again, A minus C is not possible. Why? Because they're not the same size, right? Matrix A is a 2 by 3, and matrix C is a 2 by 2. So this cannot be done. Okay, now, this is called a scalar multiplication. Example 5. Okay, here's the definition of a scalar multiplication. The product of a scalar K and a matrix X is a matrix K times X, in which each element is K times the corresponding element of X. Let's do example 5. So they want you to find 6X, right? That means 6 times matrix X, which in other words, you're going to multiply 6 times every element in matrix X. This will give us 6 times 2, 6 times 0, and 6 times 5. And then for the second row, 6 times 4, 6 times negative 2, and 6 times negative 3. And then here's my result. 6 times 2 is 12, 6 times 0 is 0, 6 times 5 is 30, 6 times 4 is 24, 6 times negative 2 is negative 12, and 6 times negative 3 will give us negative 18. So that's the result of multiplying 6 times matrix X. Now let's find minus X. So this is the same thing as multiplying negative 1 times matrix X, which means I'm going to multiply negative 1 times every element in matrix X. So it's going to be negative 1 times 2, which is negative 2, negative 1 times 0, which will give us 0, negative 1 times 5, which will give us negative 5, negative 1 times 4 will give us negative 4, negative 1 times negative 2 will give us a positive 2, and negative 1 times negative 3 will give us a positive 3. Here's an observation that I tell my students. When you have negative 1 or negative, right, times matrix, right, you can also all the signs from matrix X, you just switch them. For example, the 2 becomes negative 2, right, because you change all the signs. 0 stays at 0, 5 becomes negative 5, and so forth, right? So the observation is when you have minus a matrix X or negative 1 times matrix X, all you do is change all the elements, change the signs from the original matrix to the opposite sign. Okay. Now let's do example number 6. Number 1, we have here matrix A is a 2 by 2 matrix, and matrix B is a 2 by 2 matrix, and these are the elements: negative 2, 0, 5, 3 for matrix A, and 0, 2 for negative 6 for matrix B. So here it says find each of the following: negative 4A for 1, 5B for 2, and here, guys, for 3, we're going to combine them. We're going to do what we got for number 1 and add it to what we got for number 2, which is negative 4A plus 5B. So negative 4A is going to be negative 4 times every element in A, right? So negative 4 times negative 2 will give us a positive. Here we go, right? So it's going to be negative 4 times negative 2, negative 4 times 0, negative 4 times 5, negative 4 times 3. And here's the result. So negative 4 times negative 2 will give us a positive 8. Negative 4 times 0 will give us a 0. Negative 4 times 5 will give us negative 20. And negative 4 times 3 will give us a negative 12. Now let's do 5 times matrix B. Right, so it's going to be again, so we're going to multiply times matrix B every element. I believe this, but I'm going to do it in red. Right, 5 times 0, 5 times 2, 5 times 4, and 5 times negative 6. And the result, I think, will be in red. Right, this will give us 0, right? 5 times 2 is 10. 5 times 4 is 20. 5 times negative 6 is negative 30. Now we're going to add them, right? So we already know for number 3, we already know the result for negative 4a, right? Because that was the number 1. And also we already know the result for 5b, right? Because that was number 2. So now we're just going to add them, right? That was the result in blue plus the 5b, right? Which would be plus 0, 10, 20, negative 30. Now we're going to do what we did when we added same size matrix. It will be 8 plus 0, 0 plus 10, negative 20 plus 20, and negative 12 plus negative 30. And here's my result. 8 plus 0 will give us 8. 0 plus 10 will give us 10. Negative 20 plus 20 is going to be 0. And negative 12 plus negative 30 will give us negative 42. So this is a result for number 3. Okay, now matrix applications. Okay, again, recall from the first slide where we said furniture manufacturing, right? So this was the info that we got from that slide, right? Where all the model A, B, and C sofas and the model A, B chairs, right, were in the matrix form. Now this is what's going to be added. Okay, let me start from the beginning here. The Easy Life company manufactures sofas and armchairs in 3 models, right, which is A, B, and C. The company has regional warehouses in New York, Chicago, and San Francisco. In its August shipment, the company sends 10 Model A sofas, 12 Model B chairs, and 5 Model C sofas, and 15 Model A chairs, 20 Model B chairs, and 8 Model C chairs to each warehouse, okay, which it represents by the matrix here. Okay, now, let's see here, right? So for Chicago, right? So this is what it is for Chicago here on the right. C stands for Chicago. Now, during August, the Chicago warehouse of the Easy company shipped out the following number of each models, which the entries in the matrix have the same meaning as given earlier. So they shipped out 5 Model A sofas, 10 Model B sofas, and 3 Model C sofas, and 13 Model A chairs, and 12 Model B chairs, and 8 Model B chairs, right? So what was the Chicago's warehouse inventory at the end of September? Take into account only the number of items received and sent out for that month. So solution, we're going to do C minus K, right? So matrix C from Chicago minus K, which means the number of items that were shipped out. So this is my C, matrix C, minus matrix K. So it'll be 10 minus 5, right? 10 minus 5 is 5. 12 minus 10 is 2. 5 minus 3 is 2. 15 minus 13 is 2. 20 minus 12 is 8. And 8 minus 8 is 0. So this is what was left after that transaction. Okay. Okay, now comes matrix product. It's very important information here, guys. Okay, I put it with in red and also with I think like 5 explanation points. Multiplication of matrices can only be done under the following conditions. Okay, so let me show you the concept here. For example, if matrix A, right, has a size m times n, so matrix B must have the size of n times p. In other words, the once you put the size of both matrix, the 2 in the middle must match. If it matches, then it can be done. The matrix can be multiplied, and the answer will be the outer, which would be an M by P matrix. Okay, let me show you an example. Okay, now, if the size of matrix A is a 2 by 3, then matrix B must be what? All right? Right? I mean, for it to be done. So remember, matrix B must, right, the one in the middle here must also be the same one over here on the right. So this has to be a 3 by something matrix. Right, 3 by something. It doesn't matter if the number sign is a 1, 2, 3, 4, 5. It doesn't matter. What matters is that once you put the matrix, the size of the matrix, right, like kind of together, the two in the middle must match. In other words, these are the rows, right? These are the columns. So the columns on matrix A must match the rows on matrix B. And the outer number, right, then the columns on matrix B, doesn't matter what it is, right? Because as long as the two in the middle match, the operation can be done. So this is my solution. It'll be a 2 by whatever the number is, whatever the column is on matrix B. Okay, now, given the following matrices, state whether the matrices can be multiplied. Matrix A, right, this is matrix A. And this is matrix B. This is matrix C. And so matrix A, right, is a 2 by 3, right, because we have 2 rows and 3 columns. Matrix B has 2 rows and 2 columns. Matrix C has 3 rows and 2 columns. So now, can we multiply matrix A times matrix B? If we notice, right, A is a 2 by 3. Let's look here. A is a 2 by 3, right? And B is a 2 by 2. So do the middle numbers match? No. So no match. So this cannot be done. Okay. Now how about if we invert them, right? Instead of multiplying A times B, right? How about B times A? Well, let's put them together. So we have to put B, right? Since B is first, we have to put matrix B first, the size. So matrix B was a 2 by 2, and matrix A is a 2 by 3. So can it be done? Yes, it can. Yes, a match, right? So the answer will be a 2 by 3, which are the outers. How about A times C? A is a 2 by 3 matrix, and C is a 3 by 2 matrix. So there's also a match here. So yes, it can be done. And the answer will be a 2 by 2. Okay. Now let's multiply them on the next slide. Okay, now we're going to multiply. Here's how you multiply. Well, this is the way the book shows you how to multiply. Okay, I have another way which I believe it's a little bit easier, but it's real hard to put into a PowerPoint. Okay, if you ever want to come and see me for assistance at TM, or you want to come to Sunday Numbers, I can show you how to multiply. Okay, a different way, which in my opinion, or my students have told me that it's a little bit easier than the way the book does it. But I'm trying to follow the book as much as I can here. So this is the way the book actually shows you how to multiply them. Okay, so it can be done, right? And the answer will be a 2 by 3. So here's what we have to do. There's going to be, a few steps here. Okay, so step 1, right? I'm going to color code it so that way you can see exactly what's taking place. Matrix B is a 2 by 2, and matrix A is a 2 by 3, right? So here's what you're going to do. We're going to multiply the first row on the first matrix, on matrix A, right? On matrix B, the first row, you're going to multiply times every column. So for example, step 1, I'm going to multiply the first row times column 1. And then step 2, I'm going to multiply the first row times column 2. And then step 3, I'm going to multiply the first row times the third column. And if you notice, right, after I do that step, there's no more columns, right? So then I'm going to multiply the second row times the first column, second row times the second column, and so forth, okay? Let me show you by actually working it out here. So I'm going to multiply the first times the first, right, which is 1 times 2, and then plus, I'm going to add it when you multiply the second times the second, 0 times 4. This will give us 2 plus 0 is going to give us 2. So the 2 goes on that slot there, on the first slot. Okay. Now, step 2. So again, I'm going to multiply the first row, but this time I'm going to multiply it times the second column in red. So it's going to be 1 times 0, and 0 times negative 2. So it's going to be 0 plus 0. The answer will be 0. So 0 goes on the first row, second column. Now step 3. Repeat the process, but now I'm going to multiply times the third column. Okay, so it's going to be 1 times 5 plus 0 times negative 3. This will give us 5 plus 0. The answer is 5. So this element here, the 5, will be the first row, third column. If you notice, guys, there's no more rows, right? I mean, there's no more columns. So that's why now on step 4, since there's no more columns, so we stop with the first row, and now we continue with the second row, which will be in blue. And we repeat the process as we did in step 1. Right, so I'm going to multiply the second row times the first column. So 4 times 2 and plus negative 2 times 4. They'll give us 8 plus negative 8. The answer is 0. And that solution, that 0, goes on the second row, first column. Now comes step 5. Again, so it's going to be the second row times the second column in red. So 4 times 0 plus negative 2 times negative 2. This will give us 0 plus 4, which will be 4. And that goes on the second row, second column. Now step 6, which will be the last step here. We're going to multiply the second row times the third column, which will be 4 times 5 plus negative 2 times negative 3 will give us 6, right? So it will be 20 plus 6 will give us 26. And that's your solution. Okay? That's the way you multiply matrices. There's the solution. Okay, now, this is called the identity matrix. Recall from section 1.1 that a real number 1 is the identity element for multiplication of real numbers. For example, 1 times any number will give you the same number. And here's what I put here. For any real number A times 1 is the same thing as 1 times A, which will give you A. In this section, as an identity matrix is signified by the capital I, which means identity. It's defined that has a property similar to those of the number 1. For example, matrix A times its identity is the same thing as the identity times matrix A, which will give you A. Okay, now this is the identity of a square matrix. Of a 1-by-1 matrix, that's the identity. Of a 2-by-2 matrix, this is called my identity. If you notice, all the diagonals from the top corner all the way to the bottom corner, there has to be 1s. And this is for a 3-by-3, right? Again, from the diagonal from the top to the lower bottom, they have to be 1s, and the rest have to be 0. So this is called the identity. And for a 4-by-4, right, it'll be the same. The same way for a 4-by-4, for a 5-by-5. All the 1s diagonally are going to be 1s, or all the elements are going to be 1, and the rest will be 0s. Okay, now, right? Example 9. The identity will be 1, 0, 0, 1. Now, if we multiply, right, according to the definition here, if we multiply matrix A times the identity, it's going to give us back the same matrix, right? Let me prove it to you guys. Right, they're both 2-by-2 matrix. So step 1, I'm going to multiply matrix A, which is A, B, C, D, right, times the identity. So again, we repeat the process. I'm going to multiply what's A times 1 plus B times 0. The answer will be A plus 0, which will be A. So the answer is A for the first row, first column. Now, second step, I'm going to multiply the first row times now the second column. A times 0 plus B times 1. A times 0 will give us 0, and B times 1 will give us B. So the answer will be B. So this belongs to the first row, second column. There's my B. Now, we have no more columns here on the second matrix. we stop, and then we stop with the first row. Now we continue with the second row. Okay. Now we're going to multiply the second row times the first column. That's why I use a color code. That way it'll be easier to see. It's more visual for the student. So we're going to multiply C times 1 plus D times 0. The answer will be C plus 0. The answer is C. That goes on the second row, first column. Now step 4. We're going to multiply the second row times the second column. This is going to be C times 0 plus D times 1, which will be 0 plus D. The answer is D. You see, guys, there's a proof. So when you multiply any matrix times this identity, will give you the same matrix. It's like multiplying it by 1. Okay. Now recall that for every non-zero real number A, the equation AX is equal to 1 has a solution, namely x equals to 1 over A, or the inverse. Similarly, for a square matrix A, we consider the matrix equation AX equals to the identity. The equation does not always have a solution, but when it does, we have a special terminology. If there is a matrix, this means if there's a matrix A, this is the inverse. A to a negative 1 power means it's the inverse. So if you multiply the original matrix times the inverse, has to give you the identity. The symbol capital A to a negative 1 is called the inverse matrix. Okay. I know the definition and wording is kind of hard to follow, but when I show you an example, it's going to make more sense of what the definition is talking about. So example number 10. It says given matrix A and matrix B as follows. Determine whether matrix B is the inverse of matrix A. So again, if we multiply them, it's going to give me the inverse. Okay, let's see if it's true. If you multiply matrix A times matrix B, right, it's going to give you the inverse, right? And because we have a little bit of short of time, because the PowerPoint has to be like 45 to 50 minutes long, it will give you if you multiply it, it will give you 1, 0, 0, 1, which I know these two are inverse of each other, which is the I. Okay, right now, so B is the inverse of A because A matrix A times matrix B gives you the identity. Okay, now here, guys, we are going to do it. Okay, let's see if it's true. There's two ways to find the inverse. Okay, so we're going to do what we did in the previous, last week's presentation. We're going to use the Gauss-Jordan method from 6.2. Okay, which means this what's in the right, what the 1, 0, 0, 1 has to come to my left side, and whatever's on the right side, that's going to be my inverse. Okay, right. So this is my solution. So in other words, in the previous slide, if you get to multiply them, it will give you 1, 0, 0, 1. But here, guys, I'm going to show you the Gauss-Jordan method, how to apply the inverse. Remember in the previous slide, matrix A was the same 1, 1, 4, 2, 6, and matrix B was negative 3, 2, 1, negative 1/2, right? And I said that when you multiply them, it will give you the inverse. Now I'm going to do it another way, right? So say they give you matrix A, and you want to find the inverse. Okay, so let's see if the inverse gives you the matrix B from the previous slide, which was not negative 3, 2, 1, negative 1, negative 1/2. So here we go. Right, so this is the inverse here. But how do you get the inverse using the Gauss-Jordan method? Here it is. Okay, remember, guys, right? This the second row, second column, where the element 2 is, there has to be a 0. So I have to use row 1 to make that a 0. So this is considered row 1 and row 2, right? So I have to multiply negative 2 times row 1 and add it to row 2, right? And again, when we use step 1, row 1 stays the same, like the same presentation as what I did last week, but it was using the Gauss-Jordan method to solve a 3 by 4 matrix. right? Here's my work. Negative 2 row 1 is the same thing as negative 2 times every element in row 1. It's going to give us negative 2, negative 8, negative 2, and 0. Now I'm going to add it to row 2, which will be 2, 6, 0, 1. Right after we execute the operation, that'll give us 0, that'll give us negative 2, that'll give us negative 2, and that'll give us 1. So that's my new row 2. Now for the second step, right? The second row, second column where the 4 is, that has to be a 0. So that's the one that's going to change. So we're going to keep the same formation in row 2, right? So what's going to change, we have to make where the 4 is, the element has to be a 0. That's why I'm going to multiply 2 times row 2 and add it to row 1. And here's my work. Right, so if I multiply 2 times row 2, it will give us 0, negative 4, and 2. So that's my new row 1. 1, 0, negative 3, 2, right? But remember, these must be zeros here. I mean, these must be 1s across. That means I have to do an extra step. Let's see. So then I need to multiply this whole row 2 by negative 1/2. Right? So if I do that, negative 1/2 times 0 will give us 0. Negative 1/2 times negative 2 will give us 1. Negative 1/2 times negative 2 will give us 1. And negative 1/2 times 1 will give us negative 1/2. So this is my inverse. See? That's how you do it. Now at times, that can be a little bit difficult for students to do it this way. This is a little bit challenging for students, especially when you have a 3x3 matrix. Okay? But anyway, only for a 2x2 matrix, there's an alternative way to find the inverse, which is, this is a formula to find the inverse, it only works for a 2x2 matrix. Okay? So this is a proof here. So if you have a matrix, right? Matrix A, B, C, and D. So to find the inverse, you're going to put 1 over, this is called a determinant, which means you're going to multiply A times D minus B times C. And then this is what takes place. The A and the D, the element A and element D, you're going to switch them. Right? You switch these two. And for the elements B and C, you switch the sign. Okay? So let's execute it. Remember the inverse from before? The same matrix from matrix A from the previous slide. So this will give us 1, right? So I have to multiply 1 times 6, right? The A times D minus the B times C, the 4 times 2. And then these two, the 1 and the 6, you're going to switch them. And then for the B and the C, you switch a sign on these two across. So here we go. So this will give us 1 over 6 minus 8. So they're going to give us negative 1/2. So I need to multiply negative 1/2 times every element on the matrix. Negative 1/2 times 6 will give us negative 3. Right? Negative 1/2 times negative 4 will give us a positive 2. Negative 1/2 times negative 2 will give us a positive 1. And negative 1/2 times 1 will give us a negative 1/2. So this is your inverse. And I believe this is very, it's kind of easier than doing it by the Gauss-Jordan method. Okay? Now this is the hardest it gets for finding the inverse. But you know what, students? There's a way to put everything in the calculator. I always like to show my students how to do it in the calculator also. But for exams, they have to show me the work, right? Which they can check the work in the calculator, but they have to show all the work. Okay, now, so this is a 3x3 matrix, right? So to multiply matrix A, right? And then you're going to put the identity. Right? The identity of a 3x3 matrix is 1, 0, 0, 0, 1, 0, and 0, 0, 1. And all the ones are diagonally, right? The elements, diagonally are all ones. So again, right, by using the Gauss-Jordan method, this is going to be my solution. So the inverse will be 0, 0, 1/5, negative 1/2, negative 1/2, 3/10, 3 over 10, 1, 0, negative 1/5. This is the inverse. But how do we find the answer? Okay. Again, we have to use the Gauss-Jordan method. So here we go. This is similar to the presentation that I did last week by solving a 3x4 matrix. So now, guys, so again, we're going to do it in 3 steps, right? 3 steps and perhaps an extra step. So step 1, I need to make the row 2 column 1. I mean for the 2 is right on row 2 column 2. Row 2 column 1. I need to make that a 0. And also where the 5 is, right, the element 5, which is the third row, first column, on the third row, there has to be a 0 also. So I'm going to keep row 1. So the second row is going to change, and the third row is going to change. So I'm going to use row 1. So I need to multiply -2 times row 1 and add it to row 2. Then I need to multiply -5 times row 1 and add it to row 3. And here's the work. So -2 row 1, right? I multiply -2 times every element will give us -2, 0, -2, -2, 0, 0. Plus row 2, we just bring the row 2 over, and we execute the operation. It's going to give us 0, -2, -3, -2, 1, 0. So that's my new row 2. Now for the second part, right, it's going to be -5 row 1. I'm going to multiply -5 times every element in row 1. And this is the result, -5, 0, -5, -5, 0, 0. I'm going to add it to row 3, right? So the row 3 just comes over. That's going to give us 0, 0, -5, -5, 0, 1. So that's my new row 3. If you notice, guys, on step 2, right? Step 2, step 2, the first row, column 2, had to be a 0, and third row, column 2, had to be a 0. You see, but they're already 0, so that step is already done. So now we're going to go to step 3. Step 3 means that the 1 on the first row, third column, and the third row, third column, the -5, the element -5, those must be zeros. So for step 3, we're gonna change row 1, right? And we're gonna change row 2. Okay, so we're gonna multiply row 3, right? Because I need to make that a 1, right? So I'm gonna just keep row 3 how it is, but I need to multiply 5 row 1, right? 5 row 1 and add it to row 3. And here, guys, I'm going to multiply -3 row 3 and add it to 5 row 2. Here's my work. So let's do row 3. Right, row 3 stays how it is. We're going to add it to 5 times row 1. So 5 times row 1 will be 5 times 1, 5 times 0, 5 times 1, 5 times 1, and 5 times 0. And 5 times 0 will give us 5, 0, 5, 5, 0, 0. That gives us 5, 0, 0, 0, 0, 1. Okay? So that's my new row 1. Now for the second step, right, and for the second part on step 3, if I multiply -3 times row 3, is multiplying -3 times every element in row 3, which is 0, 0, -5, -5, 0, 1. Once you execute that operation, it's going to give us 0, 0, 15, 15, 0, -3. Then you're going to add 5 row 2. Right? So when you multiply 5 times row 2 will give us 0, -10, -15, -10, 5, and 0. -10, 0, -10, 0, 5, 5, and -3. That's my new row 2. If you notice, the ones that, all these diagonally, right? All these must be 1s. And if we notice, all these have to be 1s, right? And the rest are 0s, which means the rest are already 0. So the only thing I'm going to do is I'm going to multiply by the reciprocal of 5, right? So for example, on row 1, I need to multiply 1/5 times row 1. And then to make that right, and then if I do that, that's what I get, because 1/5 times 5 will give us 1, 1/5 times 0 will give us 0, right? And so forth. And then 1/5 times 1 will give us 1/5. Then I need to multiply row 2 by negative 1 over 10. And if I do that, that's my result. And then I need to multiply negative 1/5 times row 3. And once I execute that operation, it gives me 0, 0, 1, 1, 0, 1/5. So you see there's my identity. And that's, let me go back. And this is my inverse. The inverse is 0, 0, 1/5, negative 1/2, negative 1/2, 3/10, and 1, 0, negative 1/5. and for a 3 by 3 matrix, there's no other way to get the inverse. You have to do it this way. Okay? And I believe that's it for my PowerPoint, and I finish in time. Okay? So, like I said, if you want a copy of this PowerPoint, you can email me at aisasi@epcc.edu, or you can also see the recording. Okay, but if you want a copy of this PowerPoint, that way you guys can go at your own pace. Just send me an email, and I'll be more than happy to send it to you. Thank you for attending my my workshop, and have a wonderful weekend.
Thank you so much, Mr. Isasi. That was a wonderful presentation on matrices. Next week, we will have in the Happy Math Hour, we will have exponential and logarithmic functions in Math 1314 and Math 1324, basic metric operations and inverses. Okay, and so thank you, Miriam, for sticking around throughout the whole presentation. If you have any questions for Mr. Isasi, make sure to email him, and have a wonderful weekend.